So good morning, everybody, and welcome to the third in the series of questioning machine safety integrity. This presentation is actually broken into two, so the next presentation will address the second half. So this is part one, talking about guarding and interlocking techniques. So just a quick introduction to those people who haven't seen the previous ones. My name is Tim Hall. I'm the product manager for IDEC in Europe, Middle East and Africa. I've got about 25 years machinery safety experience behind me, working both for manufacturers and development of products and machines, and safety devices, but also risk assessment, allocation of safety functions on machines. So very practical design experience, working on new machine development and remediation. And I'm part of a team, I'm part of an IDEC safety team, a specialist who understand the problems that you have to build your machines or to integrate machines into your lines in your manufacturing plants. So we'll be talking now for about 25 to 30 minutes, and at the end, if you want any questions answered, we've had one or two sent through already, then by all means feel free to ask questions. So let's move on. So previously, in the last presentation, we discussed the control integrity of your machinery. So we looked at the performance level and how to achieve that and all the characteristics that were necessary to understand to make that happen. But in this part one of two, we'll be looking at the mechanical input devices of the ILO, the input, logic and output. So first of all, 7 fundamentals that you need to put between you and harm. And I'm sure we can all look at that drawing on the right hand, the video on the right hand side, and see what could possibly happen. But we can all have a guess about what could possibly happen, but we all have a pretty good idea about what will occur. We put the separation techniques in place to ensure that we don't get exposed to harm. And to do that, we have to identify the hazards that exist on the equipment, with the equipment throughout its entire life cycle if you're building machines. And then we have to address all of those hazards that exist: electrical, thermal, biological, chemical, physical, mechanical, hydraulic, noise, and it goes on and on. And the only way that we can actually fully identify that is by performing a full and detailed risk analysis. Once you have done your risk analysis, you then structure a safety requirement specification, which we covered in the first webinar. And the safety requirement specification lays out the requirements to make your equipment safe. So it's not a case of we've got a door guard and we need a switch. It's we have a hazard. The separation is by application of a method of mechanical separation. We need to interlock it. So it's really important that we do it by risk assessment and not a hunch. So do not shortcut the risk assessment phase, because it is an iterative process and you will go back and use it in your validation. So what is the route to selection of good and useful interlocking devices? Well, the good news is that we have the Machinery Directive, which I've talked about many times before. And in there, it clearly states that moving parts of a machine must be designed and constructed in such a way as to prevent the risk of contact. And it must not lead to an accident. And where the risk persists, you have to have a guard fitted and potentially protective devices that separate that guard. So within the Machinery Directive, there is a harmonized list of standards, and the one for the safety of machinery of interlocking devices is EN ISO 14119. And the principle is that you use that standard to select and design the application of your interlock that you're going to fit on your machine. And the nice thing about the European standards is that if you follow the standard, it allows you to presume conformity to the Machinery Directive. The standards, and I have to be very clear about this, propose the minimum requirements. So when I see people with machine guarding that is barely achieving the requirement of standards, I often question whether or not they did a risk assessment in the first place. And whenever any of our safety specialists attend site or look at an application, you will be asked the question, have you done a risk assessment? And if you haven't, we will stand there and do, let's call it a pocket risk assessment with you, and propose ways that you should be starting to work before trying to choose a safety product. Now, I have to emphasize that the selection of safety products from catalogues is a long way down the chain of things that you need to do to make a machine safe. Coming back, do your risk assessment, select your protective technique. But there's more than just that one standard. I've just taken a few here, but these are the most common ones. Clearly 12100 will identify you the hazards that exist on the machine and gives you a means of evaluating the risk that they pose to the operator using it. But it's not just the operator, it's the people who are moving around the machine. And for that reason, you have guarding from EN ISO 14120. And if you're choosing a guard and you're selecting a technique or you're selecting a type of material, you need to understand the safety distances that the guard is positioned away from the hazard. You need to understand the speed of approach that the person who goes into the machine is actually moving at. If the machine is moving extremely fast, is it going to come to a halt before the operator has been exposed to that moving hazard? And if you're bringing a machine to a halt, it's very often the case that you're controlling energy, and you're controlling that through a means of shutting down or isolating paths. And those isolation paths and control techniques are detailed in EN ISO 13849 Part 1 and validated in Part 2. And that's particularly important because when you start talking about the approach speeds, you're now talking about controlling the devices and their reliability and how they perform. So that standard allows you to assess the performance levels of each of the devices that you are now relying on, and the input, logic, and output combine together to create three systems that join up and ensure that that machine has stopped at the appropriate time when you gain access. So what is the hierarchy? There is a hierarchy that we have to go through. And first of all, when we have a sheet of white paper, if we want to make, I always think of this one because I've seen it before, if we want to make pizzas, could we make pizzas at an industrial level without using a pizza press? Probably unlikely, but it should be considered. Is there a way of shaping the dough in such a way that it would design out the function and actually make it irrelevant to the manufacturer of that process? And that is number one. Once you've actually done that, then you need to try and look at the hazards that exist that have been identified in the risk assessment, detail them, and look at whether or not you can improve the functionality to create the same thing, the same effect. So I'll take one example. We have a square-edged pin going down through a hole, and if I were to catch my hand in there, that square-edged pin would sadly rip the end off of my finger. However, if I make the first 20 to 30% of that pin tapered, if my finger were to be caught, it gives me an increased chance of escaping because the tapering will create a gradual and progressive pressure rather than an instantaneous shearing. So simple examples like that can be applied. And when you do that, you start to reduce the risks at each point identified in your risk assessment. But eventually you get to the point where you know that there's still a depth point and it still could create quite a severe injury. So you need to introduce separation methods. And we do that with guarding. We can add safety gates, which allow access in and out of the guarding. Or we might do it without, in fact, using any mechanical or physical separation. We may do it with presence sensing devices such as light curtains or laser scanners. But in each case, it creates a separation between the hazard we've identified and the person who is using it. And I have mentioned operator quite a few times, but it could be anybody using the machine at any life phase, or in fact, people just in the vicinity carrying out their other tasks and duties. So once we've got the gate interlock, or we've got our presence sensing device, we then have to move on and look at the safety related controls. We need to ensure that the input and the output devices of the machine are monitored and perform their task correctly. During the design phase, we verify the performance level could be achieved, the PLR, the performance level required. And then at the end of it, we go back to the risk assessment, we go back to our safety requirement specification, and we validate the installation. Now, I can tell you now that I would say 90% of the applications that I've looked at in an industrial environment, not necessarily at a machine builder, they have not validated the installation. That's particularly important that you go back and perform the iterative process. And then, once we've got all our guarding in place, we've done all our monitoring, we can apply signage and we can indicate clearly what the hazard is in such a way that everybody can understand it. And those signs should be done in such a way from the standards so that there are no language barriers. It's very clear that you will get your fingers caught in these sprockets and cogs. The signage is essential. And then above all of that, and the last layer is provide PPE, protective equipment, that gives the person the best chance of not being exposed to the hazard in the very last effect. Finally, training and supervision, probably should be another line, but training and supervision. Tell people what to do, demonstrate the limits of the machine, and make sure they understand the limits of their responsibility. So technical operators should not be going in and adjusting times on safety relays and this type of thing. So training, supervision is the last protective measure, and it is not the first. It's only too often that I see people take the shortcut and go straight for wear goggles and don't go in there. That's not appropriate. The protective functions should be applied, and the management functions should be there to cover the things that slip through the gaps. So, what are we looking at in 14119? We're looking at guarding and interlocking with or without a locking function. We look at escape release. So if someone is entrapped in the machine, what do we do to open the guard and get out? We have to consider the physical conditions that these interlocks and guarding devices are being used in. We have to identify whether or not there would be resistance to defeat and whether there's a reason to defeat a guard. And that very often comes up in the risk assessment. And just as on a light note, if you ever don't believe that a guard is being overridden, just go up to the machine, look where the footprints are and the hand points are, and you will find out where that guard system is being overridden. It's always a telltale sign. We address coding and the coding of the devices to ensure that it can't be overridden with simple and means that are in the workplace. But we also have to talk about fault exclusions. These are errors that occur but are unlikely to occur in such a way that would affect the safety of the machinery, and highly unlikely. We'll come on to that in some more detail in the next presentation. We look at the basic principles of applying the devices and the functionality of interlocking and the allocation of the interlocking types, because there are 2 or 3, 4 different types of interlock that we have to address. And we also have to talk about holding force, mechanical and electromechanical, and signaling when the door is shut. So a few moments ago, I mentioned about the interlocking types. Well, there are 3 basic types, with A, B, and C. So we have type 1, an interlocking device, uncoded, normally would be a cam-operated device, which can detect whether the guard is open or closed. It has some issues with it, which we'll talk about under fault exclusion and common cause failure in a while. And then we have the type 2 interlock device. That's a coded device in some way that can't just stick a screwdriver in, you can't stick a hair clip in there and make it work. It has to be what is known as tamper resistant. That's a very common device, very often used, perfect for use on small to medium-sized machines, but also on the larger machines, you can simply increase the rigidity and the strength, and you can add further mechanical means as well that put the door action in a shear and then the switching action in a more linear path that is not exposed to the same level of force. So engineering design and how you apply it, particularly useful. And then we have type 3 and type 4, coded and uncoded. So magnetically operated switches, perfectly acceptable to be used in a safety environment. They have to have means of protecting their internal contacts. The clue is in the name. They are non-contact switches, which means that when the door shuts, there should be a buffer, and that buffer should prevent the devices from coming into contact with one another. They are incredibly reliable. They have a very high switching frequency and have a very high lifespan, provided that they remain not in contact. If you smack them together, then you have a risk of a fault occurring. And in particular, if they haven't got their own internal integrity or their internal diagnostics, there is a risk of failure. And so very often you'll find them dual channel and monitored by safety relays, which we will come on to talk about. But then with the coded devices, we've got encoding, unicoding or standard coding, where we have the device actuated by a unique product that is fitted on the door guard and cannot be tampered with magnets or other causes. Now, with a magnetic switch, of course, if you bring a magnet up to it, it's quite possible that it might operate. So the physical position of that switch is essential, and how you do it is laid out in the standard. But most importantly, for all of the non-contact devices, is a sweeping action that, if it is not coded, pushes away anything or any actuator or any tampering device that's been put in place. So it's a clean sweep each time you open and close it. Positioning in the guard slots and how that is done up and out of the way is very important. So I probably already talked my way through this slide, but fundamentally we've got mechanical and non-contact switches. In the non-contact, there are lots of different technologies that are acceptable: inductive, magnetic, capacitive, ultrasonic. Of course, you can use optical. What is important to remember is, with devices like inductive, if there is a risk of an accumulation of ferric material, it could in fact cause a nuisance tripping. So it's very important that every single time the door opens and closes, that sweeping action takes place that creates that removal of anything that might be built up. So uncoded and coded devices. When we start talking about the coded, you can code up with multiple magnets, with north and south, south, north, and so forth, normally about 5 or 6 pairs of magnets, all operating in a different way, but when they're switched together, their common signaling gives you 1 or 2 channel output. And with the RFID, the tagging gives you similar to all of the tagging that you see on the products around the world, but the coding is set in such a way that as you tag, it is unique to the application, and somebody can't come up and just bring another actuator up. So let's just go back to the very beginning. And if you have a limit switch fitted onto a machine, you see it all the time. In fact, in some of the standards for presses and for injection molding machines, it's the prescribed method for utilization on a machine. You can fit 2 limit switches. But if you apply a single limit switch, then that has to have direct opening contacts. And a single non-direct mechanical action must not be used. It has to be paired with a direct opening device. And a direct opening device is defined by the little arrow symbol. And as you slide the door guard across, the leading edge of the door guard compresses down and forces the door open, and the switch contacts open. And the switch that's following, trailing down the bottom, for example, here, as it follows, the spring pushes up. That is not a safe function, but the primary safety function has been taking place in this position. And then when we close the door back into the run state, we are then using this leading edge to compress down the switch. And if there is a problem, it will break and separate the contacts. So why do we do that? Well, it's to prevent common cause failure, because roller limit switches, as they stand on their own, have many things that can go wrong with them. The worst case thing that I see is a single switch being fitted with just 2 fixings. You only have to undo 1 switch and you have completely defeated it. Sorry, 1 screw and you've completely defeated it. So 4 screws applied properly and 2 devices monitoring both the forward and the backward travel gives you an excellent dual channel, dual switch means of monitoring. So let's have a look at the guarding and the definitions. I think this is really quite basic. Yet every week I go into factories, pre-COVID, every week I go into factories, and I see the same problems time and time again. So we'll go back over these points now. Fixed guard with screws, nuts, or welded into place. It can only be opened or removed by the use of tools or by the destruction of the fixing device. So it's pretty clear. You cannot just wander along and unhook that guard. Fixings must remain attached to the guard in place. So when you unscrew it, the fixings have to remain through the metalwork. And that's normally done just by adding like a crinkly washer on the back. And then when you take it off, all of the screws go with it. Well, why is that? Well, in simple terms, day 1, it's got 6 screws. Day 10, it's got 4 screws. And finally, it's just got 1 screw left on the top. So having them in place means that it is put back on properly. And if they are fixed, if you don't do them all up, then the guard will be projecting and will have to be screwed down properly. It's very visible. So where possible, you should not be able to have the device that hanging in place. So things like keyhole slots are just not permitted. You can't just hang a keyhole slot on and then unhook a guard. That's a movable guard and we can't have that. And if you look in the drawing in the top left here, I put a little yellow circle. That is the absolute worst place you can put a fixing on a machine guard, top dead center, because I can assure you that after 6 months of being installed, all the screw have been removed during maintenance. They've been lost, dropped on the floor, and the only screw that remains is the one in the middle. And then, of course, that guard is now just swinging, hinging out of the way. I wish I was joking, but I've seen it over 100 times in reports that I've written. So simple practice, put your guard fixings in the corners, make sure that you can't use just one fixing to retain it in place. Then we get on to adjustable guards. This picture, I should have put a credit in here, is courtesy of the standard. Adjustable guards restrict access and can either be done manually or automatically. So for example, on a drill press or on perhaps a fixed application on a milling machine, the guard will automatically go up and down as the drill moves in and out. So gravity allows it to slide into its tapered fitting. And it should be readily adjustable. Easily adjustable without the use of tools, so you can preset it so you can perform your task. Now, in the world of safety, we do live in the real world, and we accept that this job today will be different to the job tomorrow. So the better the adjustability and the better that the application is for putting the guard in the location where you think the hazard or the parts are being ejected, the better it is. So it's okay to use adjustable guards, but most importantly, training and supervision, making sure the right people know properly how to use this. And you'll find normally in an engineering workshop, within their risk assessment, they have skills matrices which detail who can do what tasks and whether or not they're authorized to perform that use. And then we have interlock movable guards. And those guards have to ensure that the hazardous functions that exist on the machine are in an off state if the guard is utilized. If the guard is opened, then a stop command has to be given, and that stop command has to shut down the hazardous motion. And we start to consider here about the distance between the hazardous motion and the active moving components that are going on inside. And those robots in there could be moving as much as 10 meters a second. Also, they have an extremely large swing radius. So have we taken that into account when we've been looking at our standard 10218? Where are our guards in position? How quickly do they come to a halt? And if you look in the illustration there is in fact a robot extremely close to the door. So when I open that gate, we have to get feedback into the control system that identifies that the hazardous motion has gone away before the gate is opened and we're allowed to go in. And we also take advantage of signage, of course, and also gain access through lights and indication on the machine. But we also have to think during our risk assessment, how many people are working in the area? Can they move from one location to the other? Can they move through from one position into the other in the machine? Are there multiple people? So once you get into this movable guarding, you've then got to consider the zone of control, the zone of control of the emergency stop, and then consider how far people can progress inside. And then you consider where you locate your reset button, because can you see a man lying behind that car or a lady lying behind the car? Of course you can't. So it's quite possible that you may need to position resets which give you visual control over areas that aren't normally visible from that point of access. So as you enter in, you have to consider, as you exit, you have to consider, have I checked the zone? A lot of areas like that with multiple hidden areas are best covered with the use of laser scanners. The mechanical guarding can be in place for high-speed operation, and then maybe you use the laser scanner or something like that for programming or stepped control at low speeds, and in this instance a maximum of 250 millimeters per second. So you have to consider how you restart and re-energize at the end of using that door guard. So some interlocking definitions. So interlocking, I've probably already covered this, is mechanical or electrical or other means to prevent operation of hazardous function on the machine. Now, in general, people look at this and think electrical interlocking, but it could be mechanical. It could be absolutely mechanically keyed in. Something like removal of energy using a key, and then that key opens a gate, and because the power is dissipated, we've got access. So don't just think about electrical control, there can be mechanical as well. So a guard locking device is one intended to lock and or interlock the guard in a closed position. Of course, they can be completely integrated into one, but it's not mandatory to do that. You could use a shot pin and you could detect that shot pin's position. We'll talk about that in a short while. And then electrically monitor that back into a safety related control system. And so your guard system has to be linked up with your safety control system, which is to EN ISO 13849. It could be to IEC 62061 for electronic programmable equipment as well. But I have to emphasize that where we have electrical and programmable equipment, because the guarding is invariably mechanical, you tend to default back to ISO EN 13849. So direct mechanical action is a positive action where mechanical component movements result in another mechanism being moved or actuated. And it's done by rigid means, and no spring actions, no snap actions, no elasticity that results in a movement. It has to be linked. I'll give you an example of that on a what I would call quite an old school design, but still very valid, is on reciprocating presses. You have a guard, and the guard is mechanically linked via an armature to a very secure scotching pin. If the guard is open, the clutch mechanism of the press is completely disengaged, and you have to have the guard in the closed position with a mechanical linkage, which then re-engages the clutch pin. And therefore, your rigid elements have prevented any rotation. And then we've got direct operation. This is the most common thing that you see in the safety switches, especially with the mechanical ones. And that's a contact separation as a direct result of the movement of an actuator. And the actuator does not depend on springs. Okay, we cannot have any spring movement. So just a quick fly through here on actuation means actuators have to be done in such a way that you can't tamper with them. You insert them into the switch. You go into the actuation system, which is invariably on a rotary cam mechanism, a couple of locking cams, and a main drive cam that presses a plunger forward and forces the contacts in the output section apart. So the movement of that door has a direct action on the separation of the contacts. In principle, this is very simply demonstrated here. If I take a hinge operation onto a limit switch, the high point of that hinge and on that cam mechanism there presses down and creates a forced disconnection. That's how it works, very simply. Non-direct methods should not be used as a standalone. I've mentioned that you can do two together, but you should never have a single limit switch operating in this way, because if the roller breaks, the screw comes undone, the cam locking mechanism comes undone, you lose the indication and position of the door. And therefore, I still see it. It still does exist on old machines, and if you've got machines like that, give us a call and we'll come along and give you some guidance on how to put that right. So the cam action should be positive, and you see if you break one of the safety switches apart, you see that in all safety switches, whether it's tongue actuated like I showed you before, or rotary. So just a quick recap. Protective fences must ensure that there is no way into the hazardous zone, and if the guard is open, the mechanical actuation of the safety switch stops the machine in time before you gain access. Every garden fence must have a mechanically actuated device on it, but that could also be a coded device, which we'll talk about in detail in the next presentation. And the basic requirement is, as I've already said, open the door and the machine comes to a stop. So interlocking selection criteria start with risk assessment, like I've already talked about. We've looked at our guards and we've decided that there is a requirement to have access into that location. If there isn't access into that location, then the guarding is bolted and would normally only be removed for major unexpected maintenance. If there is maintenance requirements, you should be able to gain access through the doors and do quick maintenance. We don't want guards being removed for minor interventions into machines. If we are removing guards and taking them away, then there should be a separate and deliberate lock off, tag out procedure, because it is likely that that guard is going to remain off and the hazards will increase. Again, this should be detailed in the risk assessment. Very important that we address the stop time of the machine and the approach speeds and the reach distances. It's no good putting a guard in place if we can reach over and reach the hazard. So in the next presentation, we will actually be covering the stop time calculations that relate to the light curtains and laser scanners. And most importantly, we've got to also address the fact that just with a basic mechanical guard, you can still gain access to a machine before it's finished, especially if it's a hinged guard and they're very large. You can open a guard. Every device has what's called a hysteresis, and if you open them simultaneously, you can get your hand through that guard in sufficient time to reach moving machines. So stop time tests do not only apply to protective optical devices. Excuse me, just take a quick drink. And of course, I mentioned already, if you're controlling, then you should be looking at 13849. So what's the flow chart for selection of a lock or not to lock? It's pretty simple. If you can gain access, then you should use a lock if there is a rundown time. You need to identify how long that is, and then through your control process, control the signal that goes out to the solenoid locking switch to prevent access to that. If it's instantaneous, no problem, just use an interlock like you see on the right-hand side. So with the guard locking, there are a few things that we should address. When the actuator passes in and out of the switch into the closed position, it has to ensure, that the cam has rotated and the spring has pushed the contacts together. Now I emphasize there, the spring brings the contacts together, and it is the opening and the rotating of the cam that creates the separation. So if we've got welding going on at this point here, the physical rotation of the cam will provide sufficient force to snap those contacts open. And one term that can be used for that is bifurcated contacts, which are basically like a mechanical fuse and have a narrow waist in the middle. And when the cam pushes, if it's welded, it will snap it open. And you may wonder why your machine won't restart. It's because your contacts are broken. So we're looking at spark erosion on the contacts and what can we do to protect that? So we're looking at inductive in our control circuit. Are we fitting snubbers or diodes there to make sure that we've got the best possible switching conditions for our safety devices? Again, It's basic, well tried and tested principle, but if you're drawing an arc across a contact, you are eroding it, and eroded contacts will weld and fail to danger. So make sure that you've got your basic principles of your control circuit sorted. And then we've got a mechanical spring. Well, of course, if the spring decides to lose its springiness, or for some reason a manufacturing product has got in there, it may actually not compress. So by having that mechanical fuse, if it doesn't compress, the contact will separate. These are all fundamental design criteria for safety switches, but in this instance for the locking of a safety device. Now this bit causes a huge amount of confusion. Do I use dual channel, or do I use dual channel safety with single channel monitoring? Well, it really comes down to risk assessment and what you want to achieve. But what you have to remember is for the actuator that is passing in and out, it will create a separation of these contacts and switching the auxiliary when you open and close the door. When you lock the door, and that is the motion of changing the solenoid, whether it's power or power off, I'll talk about that in a moment. When you lock the door, you have got this linkage here, which shuts these two contacts. So door closed must not lead to the start of the machine. It has to be door closed and verified as locked. And if you're on a high-risk machine, it makes sense to have synchronous switching between the actuator and the solenoid, and therefore they are wired in series. For a slightly lower risk machine, it's acceptable to have less lock monitoring and dual channel going on the front end, on the actuator. But there is an electrical and a mechanical linkage in both that determines that the door is shut and that the signal can then be sent to the control system to remove the locking feature, and then the door is shut and you will not be able to gain access. And you will have to send a fresh signal to that door in order to be able to open it. So, most important is verification by electrical and or electromechanical means to make sure that that door is in the correct state. Periodically, you will come across machines that have got this linkage completely removed. And they do that so that they can have dual functionality. During low speed setup with semi-automatic setting and guaranteed low speed, they can shut the door and do inching and checking and jogging. And they can open the door without the need to keep pressing the button. And they do that by separately monitoring into two channels this pair, and then separately monitoring this pair into two channels, and they remove the links. And what you do is you use something like a safety PLC to actually reinstate those links for fully automatic. So for setting, you remove them, and for fully automatic, you put them back in again. Now, all of that is subject to meeting the correct requirements of performance level, but it is quite common to see those links removed. And most manufacturers, including ourselves, have those links removable. So, principles. Power to open means no volts, and then we apply power to the lock, and the lock comes open. It's pretty straightforward. Energize the solenoid, pulls the pin back. In the standard, it's drawn like this, which is just an actuator going backwards and forwards. And it's the most normal way to do it. About 95% of applications is you power it up, you apply a signal, and it opens. But you can also use power to keep it closed. So in that event, we apply a signal, that signal voltage sends it forward against the spring, but then we're relying on the spring to open the door. But we're also recognizing that in a no volt situation, it could in fact spring open. And we need to recognize that in our risk assessment. And it's for that reason, only about 5% of applications actually use power to lock. The norm is power to open, because in the event of a failure, that door will remain in the lock state. So 95%, 5%. But there are reasons. There are times when people might need to do it. Most importantly, it doesn't matter how this works with a pin, but that pin can only be ejected forward into the location. It cannot ever be ejected into free air. If you put it out into free air, it's missed the lock location and it is a dangerous application. And for that reason, that pin has to be monitored in the forward state, like I said in the last slide, electrically and or electromechanically monitored, so that we know that it's in the lock state and not just sticking out little bit like a door being held open and somebody releasing the button on an apartment. We can also do the same using fluid power. By fluid power, I mean the use of hydraulics and pneumatics. That's quite common in presses, where we apply hydraulic fluid. It locks the door in a conditioned state with air, but we also again have to monitor the forward and backward state. Now, you shouldn't be monitoring the valves. You should be monitoring the actual position of the plunger and whether or not it has been engaged. So the mechanical design requires a little bit of work if you're just using plungers. Now, this is something that is actually really useful. It's a mechanical time delay bolt switch. Doesn't require anything other than you go up to the machine, and if you undo the guard, the first, I think it's 1.5 turns, creates the pressure on switch number 2, and the high spot disconnects the safety circuit. But because of the pitch and the length of the thread, it winds it back out, and it's still not engaged. And you have to wind, and then eventually you've actually removed it far enough that you can open the door guard. They have their place. You often see them on the side of high-speed rotating saws and band saws and that type of thing. It's very common with a threaded exit. Sometimes you see threaded with an auxiliary or a secondary switch, but what you will often see is they're put in a corner or they're put next to a post. And when I say a post, I mean a mechanical obstruction quite close to where the thumb wheel is. And the reason for that is because one of the first things the apprentices learn is if you wrap a piece of string around it and pull it, you can spin it at high speed. If you spin it at high speed, you've overcome the time. So it's important to make sure that the devices have anti-spin, so they put friction material in. And again, as I said in the previous one, it's important that you cannot let that go back out into free air. So it can only be obstructed if it's on a hinge guard. The only place that it can ever be ejected forward is into the pin when the door, into the hole when the door is in a closed position. So what can we do for a conditional access? Well, certainly something that we see more and more of around Europe, and maybe slightly more of a British thing, but you see high quality control access locks, which can either isolate a 2-channel safety circuit or in fact isolate the power, air or hydraulic power. And you can take that key off to a key exchange. So once you've isolated the power, you then migrate the key to a location. You put that key in and turn it, and then that frees up another key. So from there, that free key is taken into here, and then that allows up to 3 operators to remove a key, place it about their person, and go inside. Now, I talked to you earlier on about reset controls. There are no reset controls here. Simply the fact that the primary key over here cannot be released unless all of these 3 keys are returned to their base station. Once they're replaced, we can then take that key out, put that back in there, put that back in there, go back to there, turn the key, and we can restart the machine. And that can be restarting just by putting the power on, or like I said before, safety-related control. It's a very reliable electro or purely mechanical application. Also, the release of the key, like with the solenoid lock, is associated with a safety-related control, and it could be that it's time delay. So providing that time delay gives the additional reaction and then delay for the hazards that exist on the machine. And similarly, we can do it like with a control release, key operation, and go in, and you can't open the door or the solenoid locking. Even if the solenoid is locked, you still need the key to do it. So there are other ways, especially during mode change and that type of thing. This one's pretty straightforward. You see it on security gates, huge magnets, rare earth magnets, and we apply a voltage to a electromagnetic coil that swamps the holding action of the rare earth magnet, and that creates a weakness, and then you can open the door and go in. And within that, there are contacts or separate contacts, depending on how it's configured, to provide you with an opening condition. So your operator's working inside and somebody shuts the door. The voltage is off the coil and we now have a dangerous condition. That will have been determined by the risk assessment. But there are measures that you can put in place to make sure that people don't get trapped inside. And that's emergency breakout or emergency locking release. And you see in the picture on the right-hand side, the panic button. As the person wants to leave, you hit the button and exit. I have to emphasize that door guard must open outwards. We do not want people hitting the button and having to step backwards deeper into the hazardous zone. It's really a case of smack the button, leave the building. It leaves them the part of the machine. And that would be, in all cases, identified in risk assessment. And if there is a risk of being entrapped, then just have that in there. You often see it on robot cells, where if something goes wrong or during programming, they can just hit exit and they're gone. So coming on to the last few slides now, assessment of fault conditions. For performance level E, fault exclusions are not permitted. So let's just quickly remind ourselves what a fault exclusion is. That is a design function within the machine, within the component, that we know that if it breaks, it would lead to a dangerous situation. But through testing and through accepted lifespan testing, we recognize that it's unlikely to happen. I'll give you an example of a fault exclusion. I've got a single contactor, I've got a 4 kilowatt motor, and I've put a 25 kilowatt contactor in there. Aging of the contactor is extremely unlikely. Short circuit effects are limited down to 4 kilowatts, so it's a very, very happy contactor. I might claim a fault exclusion, but I can't claim it at performance level E because we can't take that risk, because performance level E, you go in there, that's the last thing that you see. So if you have a mechanical interlock fitted, there are fault exclusions around the rotation of the pin and the braking of the actuator and a single actuator. So in that case, you want to provide a diverse technology, ideally, and that with that diverse technology, you've got your switching function, you've got your door lock, and a separate interlock that's going to just detect just in case that breaks. But even with those fault condition, you still have to provide, if it's performance level E, at least a monthly functional test, and at performance level D, annually. So for those door guards at the back of the machine that rarely get used, it's worth during your maintenance cycles to just go in, and before you do the shutdown, just use that door at the back and double check it. So, fault masking. We will do a detailed analysis on fault masking during the next presentation. But just to give you a clue, if you open the first door and there is a fault in one channel, the safety relay will see it. But if you then subsequently open a second or a third door, it will see both channels cleared, but the first channel fault has been lost. So it's very important that when you're configuring your safety circuits, if fault masking can occur, it's essential that you have a means of detecting it. And that could be one switch, one input, one switch, one input, or it might not be necessary because it's quite a low risk application. So be careful, because when faults occur, there can be a scenario where a second or third gate can open it up and you won't be able to detect it. And that cascading of faults only really occurs in the volt-free contacts. If you use an RFID switch, it doesn't matter so much, because the cascade is done in such a way that switch 1 powers off switch 2, and therefore the cascade is inherent all the way down the line. So, coming up in part 2, we will look at positioning of devices in the optical electro-electronic. We'll look at light curtains and how to position them and the best things you can do for use of scanners, either in static or in mobile applications. And we'll look a lot about approach speeds and also a little bit more about reach distances and we'll go into detail on fault masking. And then at the end of that, we'll draw together and summarize the 3 previous webinars, and then just put together like a little risk assessment and understanding about what's going on. So perhaps in the future, you might want to suggest a topic. We're not limiting it to just the few that we're doing here. We also just started to offer a custom rerun, because I know that some people have only joined them in the latter stages. If you want a custom rerun, we can do it for 5 or more people, or if 2 or 3 people want to get together, that's no problem. If you have a more immediate need, we do things called Coffee Tech. Since the last Coffee Tech, I've done, I think it's 11, like design reviews online with people, detailed analysis of their applications, integration of machines. It's a quick fire reference, your drawings, and I bring in the brains from around the team, and sometimes external people to help on these applications. So thank you very much for your time. I hope it's been of help to you. And if you've got any questions, that'd be interesting to hear. Hello.
Hi Tim. Another great webinar. Thank you very much for your contribution. Superb. Okay, so please, anybody, if you've got questions, please enter them into the chat window within the Livestorm platform. I've got a couple that we received before the session kicked off. So Tim, if you could first look at these. How can we be sure that the circuit is connected correctly?
Yeah, okay. That quite often is the case that I mentioned about doing a periodic test, and the safety managers require that periodic test to be done. But when it's actually being switched off, do you know that it's actually the safety device shutting it off, or is in fact just a standard control? You have no way of knowing. And the only way you can really do that is have the skills and competency to be able to analyze the safety circuit. So when you integrate safety components, when you buy in machines and you join them together, you need to ensure that you have staff on site who can do fault finding and who can actually identify, hold on a minute, that's only switching with the auxiliary. And the quick check would be, on the previous slide, I showed you a safety relay. If you open and close the safety gate, you'll see in the control panel, 2 lights go out on the safety relay, or on the safety PLC, you'll see 2 channels go down. So from the outside, to answer the question, you can't really, you can see a reaction, but you don't know if it's a safe reaction. But if you have the competency to analyze a drawing and then look at the wiring, then you can, inside the cabinet, then you can look at it that way and pick it up with the enunciation. But on the latest generation of safety relays, we actually now do data from the safety relay up to the HMI direct. So more people will be able to actually see the true state of what's going on with the contacts.
Okay, thank you very much. Next question that's in here is, when is it okay to use power to lock switches on a machine?
You're asking me? Never. But there are applications where it is appropriate. The one that I've done the most is in the tobacco industry, because when a machine creates a fault, you get a lot of highly combustible material accumulating, and if there's friction or any fire, then the instruction is hit the e-stop, turn the machine off, exit the building. That's pretty standard fire procedure. And in comes the fire officer, and if it's power to open, he can't open it, and they just go up in smoke. So what you would do is, in that instance, you have a no volt release, and by risk assessment, if you have got residual energy, then you need to fit separate and additional means, so that if you lift it up, you gain access. You can't do that. So if the power goes off, you need to have an additional protective layer separating someone to reach out. So I would say fire, perhaps where there is a risk of a continuous catalytic process, which could then generate heat You know, when you mix two-part epoxy resins, they can sort of generate heat and sometimes spontaneously combust. But again, it's down to risk assessment.
Okay, thank you. Third question is, you mentioned that interlocks, mechanical interlocks, should not be used or are not permitted to use for PLE applications. Can you expand on that a little?
Okay. You saw when I showed you the actuator going into the switch, it rotated a single cam. That cam is rotating around a single shaft. If that shaft breaks or snaps, you lose the positive action that drives the contact down. And so it's a requirement that that single failure can't lead to a common cause failure, the loss of both safety function, both safety channels. Because anywhere where there is a mechanical actuator in place, it has normally got a common switching path, a single plunger driven by a rotary cam. So if that is disconnected, then you've lost both channels, and that common cause failure can't be accepted, because at performance level E, it's open the door and that's it. You know, you're probably not going to survive. It's that kind of hazard. So yeah, and then what you can do is, like, we have RFID sensors. You don't have to fit an RFID. You can fit any other device that isn't subject to the same common cause failure. So 2 switches on the door at performance level E.
Okay, thank you. Tim, another question that's come in from Paul is, are there any changes, present or planned, in safety interlocks generally after the Brexit between the UK and the EU?
Right. We need a whole webinar for this one, but okay, this is easy. Everything that you are used to about the Machinery Directive and the European standards has been, I'm not going to say replicated, but migrated into United Kingdom law with the UKCA. And so the standards that apply to mechanical interlocking safety related control today will apply in the future, but they are held in law under the supply and machinery regulations in the United Kingdom. Now, I've still got more training to do on this, but bottom line is the principles and safety functions that you are looking at will not change, but the law no longer requires you as a British manufacturer or British company to apply to the Machinery Directive whilst operating in the United Kingdom. It is now the supply machinery regulations. It's always been the supply of machinery regulations in the UK, but with the CE marking sitting above it. Now, if you are exporting your machine from the United Kingdom to the European Union, then you will have to comply to the Machinery Directive and all of the standards that exist there as well. So standards remain the same, and you'll find if you go online to British Standards Online, who we use, you will find exactly the same standards exist today, but the legal framework is now established under British law. So great news, the answer was no change.
Okay, thank you very much. One question also, if you're a mechanical or electrical design engineer and you put together a solution for you believe to be safe, whether that's the electrical safety circuits or whether it's mechanical guarding and interlocks, should they be checked by third-party companies, or are you okay to sign that off yourself?
So you're asking if people are permitted to self-certify their equipment?
Yes, yeah. Absolutely.
Okay. If within the Machinery Directive, there are different annexes, and some machines, it's simply ill-advised or not permitted. So if it's an Annex 4 machine, for example, a woodworking machine or press tool or something like that, you have to use a notified body to ensure that your machine development is done properly. And you create a technical file, and that technical file can either be bonded by them and then taken out for inspection, or you can get that third party to come in. I'm sure you've all heard of TUV. Different organizations at TUV operate in different ways, but fundamentally you bring them in and they give you a TÜV mark. If you look at our safety products, they're all TÜV certified by TÜV Rheinland. So the issue always comes down to, am I competent to perform this task? And are there any subsidiary laws? Now, in some countries, there are additional laws which go over and above the machinery directive, which means you have to then check in your local law. But the most important thing is, if you've identified a hazard on a risk assessment and you've put in a safety requirement specification, these are functional safety standards, and part of functional safety is the delivery of skills, competency, and the management of that competency to put it forward. So if you are not competent and you cannot demonstrate, you will have an issue. Certainly, if you think about the behaviour of the British HSE, they will ask, are you competent, in the event of an accident, were you competent to design a safety-related control system and validate it and verify it? And did you do it with validation by somebody who was not involved in the project? Functional safety requires that you make your design, somebody else verifies it. You do the installation, somebody else validates it. And they have to be separate from the project. Doesn't mean they have to come from outside. You can hire somebody if you want, but as long as you can demonstrate competency, then you can do your own safety work, no problem. But not on Annex 4.
Okay, thank you.
Sorry, that was a rambling answer, wasn't it? So.
Any other questions from anybody else? I think we've covered everything that was in the chat box. Okay, thank you, Tim. A great session. Well done.
So just there, it's on the slide. If you got any questions or you didn't feel that you wanted to ask your question in public, you've got my email address. We do, every morning, we do coffee tech sessions with people. By all means, phone up, have a coffee tech. And by that, I mean, you grab the coffee and I do all the talking. You gathered I'm quite good at that by now. But it's most important that if you do a coffee tech, that you can get your drawings together and we can solve your problem for you. And then hopefully when COVID is finished, we can get on planes and cars and come and see you as well. Thank you very much.